Hello, everyone, and welcome to today's webinar. My name is Niels Betzler. I'm Product Manager Life Sciences at Qualisys, and today I'm located here at our headquarters in Gothenburg, Sweden. I'm inside our Mocap studio, so we have set up an Arcus system. We have force plates, so we can do a full data collection later on. But before we get there, I'm very happy to summarize the content of today. So first, we'll be joined by our partners from AnyBody, who are located over in Aalborg in Denmark, and who give you a short summary of what the AnyBody modeling system is. And then we move on to do a full live demonstration of a new workflow that we have prepared to streamline the data capture from data capture all the way to processing in AnyBody. And then we'll wrap up with a Q&A session. If you have questions at any point during the webinar, feel free to press the Q&A icon at the bottom of your screen and just type in the question, and either the Qualisys or AnyBody team will do their best to answer them live directly on the chat. And at the end, we also leave some time for additional questions, and we'll also pick out some of the questions if we have time to do so to repeat them. Now, I'm happy to hand over and introduce Søren Tørholm, who is Head of Services at AnyBody. And Søren will give you an introduction of the AnyBody modeling system and what its capabilities are. Søren's job at AnyBody is, like the team from AnyBody explained to me, is to bring the models to life. So he's in charge of finding the right solution for any customer questions or any customer requirement that requires modeling on the AnyBody side. So Søren, great that you're joining us today. And I can see your screen is up. So over to you.
Thank you, Niels, for the introduction. Yeah, so first I'll tell a little bit about our company. So we developed the AnyBody modeling system which is a tool for musculoskeletal simulations. So associated with the modeling system comes a full set of models, including both body models and application models, which brings these body models into actions. So these models are called the AnyBody Managed Model Repository. So we sell licenses, we do training, we do support and consultancy services using these tools. These tools is being used in all sort of scenarios. For example, of course, for motion analysis, like what you will see today, but it's also in product design and optimization. It's in sports optimization, orthopedics and rehabilitation, ergonomics with and without exoskeletons, automotive applications, and many other things. But in common of these things is that it's something the person do in a voluntarily and skilled manner. The ingredients that goes into doing such a simulation, of course, that is a fully parametric body model. And then it's some motion and some forces. And today we will feed the system with measured motion and measured forces, but these can also be synthetically created. We will also, the model also requires some sort of environment around it. And in this slide here, I'll show a lower extremity exoskeleton. But of course, in the example you see today, it's actually the environment is basically some force plates. So we do this combined model then of the environment, the body model, and the applied forces, and we solve the inverse dynamic muscle recruitment problem. So in this way we find what are the muscle forces that will create dynamic balance in this dynamic system, and out of that comes then all the internal body loads, so all the muscle forces, all the muscle activations, all the joint reaction forces, and many other properties. And of course, you can use this output in other tools, such as finite element tools, if that is needed. I think I'll give the microphone back to you, Niels.
Yeah, perfect. Thank you so much for the introduction. So yeah, like you mentioned before, what we do today is that we collect some data and run processing in AnyBody with force plates. And this is not something new. It is something that has been possible since the very beginnings of AnyBody. And in fact, some of the very first files that the AnyBody system has been used with were recorded with Qualisys. So the possibility to easily import CSV files into AnyBody has always existed. But what is different now is that at Qualisys, we have spent some time to simplify this process with the support of the AnyBody team. So what that means is that we've created an example that connects the data collection to prepare the data and to process the data and have it ready for processing. It looks like the following. So bring up my screen. You can go up to our GitHub repository where Qualisys is publishing a lot of different examples and material that we publish to make it easy for you to use the system with many different third-party applications. And the reason we do that on GitHub is that we don't just want to give you a black box that connects two pieces to each other, but we rather want to provide inspiration and examples that you can build on yourself, that you can modify, and you can give us feedback. You can make pull requests if you are into like really like changing the models yourself, changing the examples yourself. And one of these examples now is called the PAF AnyBody example. So I will open up this example, and you can see here it's a source code, it's a short introduction, there's a short tutorial video, how to use it, and I will download this example. So you just click code and download the zip file. And then when the download is completed, we'll just go to the folder and unzip that folder, that file. So right click, extract all. There we are. And inside this folder, you find a QTM project that we have prepared for you. And you can open that project either by just loading QTM and navigating to it, or a small shortcut is that you just double click the settings file. And what you can see in this is that in this project, there is a pane on the left-hand side. And if you're not familiar with this, this is what we call the project automation framework. This is a place where you can manage participant data. So you can see we've already included one folder with John Doe and with some example files. And today we will record another one and create another example. This is an alternative way to collect the data and to structure the data right away while you are collecting it. And it also allows you to connect certain actions that will run when you're finished with the data collection. So you can click, you will see that you can click on Start Processing. And then in this particular examples, the files will be exported to C3D and some templates will be populated with the right information that is needed to process the files in the AnyBody software. Before I do that, one important thing is that I just opened up this example project that I opened from the repository. And of course, that does not include the camera settings of our lab. So I have to go and say import settings from another project. And I'll pick a project where I know that it has the right camera settings, it has the right force plates already included. And after I have done that, I know that now this example project is still the same example project, but the camera settings and everything have been imported from a file that has been used with this particular camera system before. Now I will add a session for today. Sorry, wrong click here. I'll add a participant. For today, let's call our person today William Webinar. I happen to know that he's 1.83 meters and 71 kilograms. Okay, so now I have a folder and I'll add a session. And here you can see that the example we prepared supports different marker sets. I will give a quick overview of what they are. One is the IOR marker set. So this marker set has been developed by the Rizzoli Institute in Italy, in Bologna, and published quite some years ago. And essentially, it's an extended and improved version of the Helen Hayes model, with better marker sets and also we think, very reasonable, good definitions of the different marker sets, of the different segments. That's one option, and that's the option that we'll be using today. Another option is to use what we call a cast marker set, which is actually created by the same people as the IOR, but earlier in time. And this is using marker clusters. So it's using plates with markers or skin markers located in clusters. For this one, we've also prepared the necessary files to run this in AnyBody. And the third one is what we call the sports marker set. So that's a rather simplistic marker set aimed for like day-to-day data collection when it's more important that you can apply the markers quickly and that it's as little inconvenience for the participant as possible. And then we sort of are a little bit more efficient, but of course have a little bit less redundancy than with the marker placement or the marker sets in the other models. Okay, so I'll go back to QTM and create an IOR session. Okay, and what's coming up next is the data collection pane. And you can see that we have prepared this project for 1 static file and 3 walking files. And this is something that is specified in a simple text file that anyone can modify for these open examples. So if you're using one of the open PAF examples, you can decide if you maybe have 3 different conditions you are testing. You can go into that settings.paf file and modify it and define these conditions, which makes it very easy for anyone who's running the Qualisys software to collect data, to make sure that no files are missing and that they are all named consistently and located in the right place. Okay, but now let's move on and record a static trial. So I'll start preview, and my colleague will step into the volume, standing there, stationary, okay, and then I'll say start capture. Okay, so we can see that almost all the markers are labeled. It's just the 2 on the sternum that we have to label manually in this case. And the example includes an AIM model, which is our automatic labeling model. And you can see that we just have to maybe label these manually here. We'll see if we also have to do that in the dynamic trials. It's also possible to train the AIM model further if needed. Okay, so we are ready for capture. Stop. And now it's up to you, of course, how much data you want to analyze. And for the purposes of this webinar, we'll focus on the contact phase with the force plates. So I'll crop the file to start just before the first foot strike on the force plates and end right after. Save. And then we'll record one more. Okay, same procedure. Just go here, make sure we've got 100% labeling. It's looking good. Then we crop here. You can also see on the fill level on the right-hand side, that's a good way to check that all the data is fully visible. That after I crop the file, we've got 100% everywhere. It was only when my colleague was entering the volume that there was a little bit missing. And then we close here, and then you can see there's a start processing button. When I click this button, it's not very exciting because it will simply prepare the files. So what is happening is behind the scenes. And when we open up the folder, you can see that if I go back to the level of the project, that there's a templates folder here. And within that templates folder, we have provided a script, which you can go in and edit if you like. But all that this script does is it loads some templates for the AnyBody scripting files that contain the definitions of what's going to happen when you analyze the data. So it simply replaces placeholders with the height, the weight, and the file path, and which of course saves you some time and makes it more, sort of a smooth process to get from data collection to analysis. When we go into the session, clicking Start Processing has created a subjects folder, and within that subjects folder there is a static file and a dynamic file as well. So what we'll do now, I'll go in and get AnyBody here, and we can just drag this across and load. And when that is done, we can first, for the static trial, run the parameter identification. This takes a few minutes, and so we use that opportunity to switch back to Søren, who will explain a little bit more about what is happening now in the background.
I mean, this slides here, it will introduce sort of to the any mocap model, which is sort of the model that this has been based on. So it runs directly on C3D input, and it can optimize the marker location and the anthropometrics of the person based on the marker trajectories, and it supports standard force plates of type 1 to 5 plus additional plates. It's possible to use it, I mean, of course, with measured ground reaction forces, but it can also be used for predicting ground reaction forces. And it's easy to set up with multiple trials and subjects. So this picture here sort of shows a screen dump of the software. So by selecting this run analysis, it will start a sequence of operations that will, I mean, first it will track the motion, and then it will calculate the forces. Of course, then there is a 3D representation of the model seen here, and there is a scripting area where you sort of, which is, I mean, defining what the model loads. And over here to the left, there is a model tree representing the entire model structure. So what goes into such a model is I mean, it's some dynamic motion capture trial data that was recorded now, and then it's the template geometry of the model. And then the first thing that happens, the step that we will skip, is the parameter identification that takes, I mean, that where the person is being optimized in shape. And that is what is shown here on this time lapse of the video here. So it shows, you know, you can see the person changing bone dimensions. You can see some markers move around. So they move into a better location that gives a smaller marker error. And that happens automatically by the optimizer. Some markers have been locked in place, so those are marked with red arrows, and some other markers sort of which are not associated with the bony landmarks, they have green arrows, and they can actually, they are free to choose a better position if that can lead to a smaller marker error. Once that step has been done, the run analysis can be executed, and the run analysis consists of a few steps. So first it will load the parameters found in the optimization. So those are the optimized dimensions. Then it will track the motion, and that is what you see going on in this video here. So here it's already sort of have loaded, you know, the dimensions and the marker position, and here it just tracks the motion in the best possible way, leading to the smallest amount of marker errors. So the distance between the fixed point on the skeleton and the free floating, recorded markers. And then, of course, the final step is to do the inverse dynamic analysis. So that's where we apply the motion we just extracted, and we apply, of course, the measured forces from the ground, and we calculate what should be the muscle actions to create balance in this dynamic system. Okay, back to you, Niels.
Great, thank you. We'll switch back to my screen. We have now loaded outputs from the process that you just explained, Søren. And what we can do here now is we can see the fitted model for a dynamic trial. I can press the play button to replay the movement or the motion, and look at it from all different angles in terms of like visualization, and to just verify that I'm happy with the results. And when you look closely, you can also see the results from this fitting operation with the red and blue markers where they are fitted and used to track the motion. We can also plot different types of data, and I've prepared 3 different charts, and maybe you can explain a little bit about what we're going to see.
Yeah, so the first one we prepared here is the hip reaction forces. So this graph shows the the hip reaction forces of the right leg in the 3 components in the spherical joint, you know, that the hip joint is. So it's the forces in newtons we see here. If we go on to the next chart,
Yeah, and I would say, yeah, you can really see that sort of the ground reaction force is very dominant in that one.
Yeah.
In one of the components.
And of course, what I should say here, I mean that the forces, of course, this hip reaction force, of course, it's the applied load. It's one component here, of course, but of course it's the muscle contractions that plays, of course, a large role in creating these forces. So this force should be quite realistic, really accounting also for the muscle contractions.
Mm-hmm.
Yeah.
And second chart we've pulled out is muscle activation.
Yeah, so it's the muscle activation for the soleus muscle again on the right leg. So it shows the individual components of the muscles that represent the soleus muscle. So the soleus muscles is split into multiple branches. So this is the activation, and activation is sort of the relative muscle load. So it's a number between 1 and 0.
Okay.
And yeah, we take the next one.
The third one is that ultimately scales to the muscle force, I guess, which you can also output, which we've shown here.
Yes. So this is the force in those same muscle elements of the soleus muscle. And of course, this is just a short glimpse of the output there. I mean, you have this output is available for all the muscles, for all the joints, and many other more things are available. It's just to give an idea of what is there.
Yeah, I was very glad for your help, Søren, to select these examples because it's, yeah, like you said, it's a very comprehensive data set that you receive back.
And of course, I should also say, I mean, it's possible to group this, I mean, to condense these data into more meaningful groups if that is needed.
Yeah, great. Thank you very much for the overview. I'll switch over here to start summarizing today's session. So while I do that, please feel free to click the Q&A button at the bottom of your screen and ask any questions that you might have. But yeah, in summary, I hope you could see that the Qualisys system, as always, allowed us to collect accurate input data. It can be any type of Qualisys system for this type of analysis, an older one, a newer one. That's no problem. And it also works with all external hardware, like different types of force plates and so on. The PAF solution that we showed offers a streamlined workflow from data collection to simulation. So you can structure how the data is collected in folders, what type of data is collected, make sure that no one in your lab who's collecting data forgets anything. And then in the end, you have it in a structured format. And with just one click, you can generate the template files that are needed to start the AnyBody analysis. AnyBody directly imports the C3D files, which I think is a big strength and very useful, that there's no need to do any conversions in between. And then you can benefit from the power of the managed model repository, because of course it's up to you to go in and change or select different types of models depending on the task that you have to solve. And you could modify the script to use that instead. Okay, so we'll make resources available on our webinar page. As always, we'll share the recording with you afterwards. But before we get there, I will stop sharing and take a look at how things are going on the Q&A. So one question is it possible to modify the marker set? And I think maybe we can both answer that. So yes. For my part, I sort of gave that answer maybe to some degree already. Anything that is running in this streamlined workflow is based on templates files that are accessible in the templates folder. So those can be changed. And I remember that there is a file defining the marker set. So I will just maybe start sharing the screen again so I can show you where that is, because I think this is a question that others will probably also have. So I will go to the templates folder. And then in here, there is a marker protocol.any file. And I can double click this file and it opens up directly in AnyBody where the definition is shown. And maybe, Søren, you can explain a little bit.
If you scroll a little bit down. So for example, if we, the first, maybe if we look at the marker called R_head. So this is sort of the code that creates a marker. So basically it says, I mean, marker placement. So it says, okay, which segment, on our model should it be placed on? Then there are some optimization settings, optimate ops X, Y, and Z. So that basically tells the system if it's allowed to, if we think this marker is placed on a fixed bony landmark that we are quite sure about the location of, or if we want some of the directions to be allowed to be optimized. So in this case here, we actually allowed it to be moving in X direction. And then we also give it some coordinates. So this S, well, it's really the position on the skull that we placed it in. So basically this piece of code is the only thing needed sort of to create a new marker in the marker protocol. So it's quite simple sort of to add more markers.
Okay, yeah. Thank you. I will go back to the question list. And another question is, if I have a data set with collected data, can I use the PAF to post-process the data and import to AnyBody? So I think, if I understand right, this data has already been collected. So you are able to import the data. You can just, instead of recording a file in QTM, you can click the button and click import, the same button that you use to record the file, and you can import them one by one. And then you can just use it to post-processing the same way. And then the only thing that you might have to do is, if you use a different marker set, like we just explained, modify the definition to make sure that the expected marker positions on the body model are consistent with your marker set. So I hope that answered your question. Let's see if
I can see there is a question about type 1 to 5 in force plates. Yeah, so in the C3D file, there is this force plate group folder, and part of that C3D format is that there is it will sort of save into the C3D file which type of plate it is, and there are different types. And we have in the repository pre-made, force plate classes that that handles type 1 to 5 in a very smooth way. So it's again a very few lines of code that is needed to create such a force plate. And if there is a different type of plate, it's something that can probably be modified based on existing plates. But usually it's not a problem.
Yeah, thank you. Exactly, and I mean, it's also good to emphasize that type 1 to 5, from our experience, should cover 99% of the cases. Yeah. And that's at least the ones that you can get from Qualisys. And we actually modified it here for this example. It was one line to switch to a different force plate type that had to be changed. Another question is, do we have to match the marker names in the template protocol to match the markers in the C2D file? And yes, that is the case. And it should be as simple as renaming it directly in that file that we just showed earlier. And so this is, I think, also a question for you, Søren. What would be a suggested marker set to assess gait with an exoskeleton? Mainly thinking about the obscured markers due to the exoskeleton. Okay, maybe the question is for both of us.
Yeah, I guess there's no clear answer to that. That depends on which markers are not visible. But I mean, as you have seen, I mean, the protocol is really flexible. So I guess it's about putting the markers where it's possible to get a good sight, and then adjust the protocol that it corresponds to that. And basically, if there's just enough markers to handle the kinematics of the model, it should be all right.
Yeah, and I would also say from our side, from the actual just seeing the markers side, it's good to emphasize we do separate the step of calibrating the marker set that we are tracking, or calibrating the skeleton in the static trial, and maybe it's possible to have some additional markers in the static trial that define the joint axes, and then additional tracking markers. And I think, Søren, that's also something that you can use, like with the cast marker set, for example, where the 4 tracking markers on the cluster, they don't have to be in a cluster. They could be placed anywhere on the segments where you have good visibilities. And then you would also only have the static trial where you need to find a way to define the joint axes. Another question is it required to use a full body model, or is it possible to run lower body only? And I mean, I can say the example is prepared for full body. That's the only limitation from us. But I think, Søren, from your side, there's probably no limitation there.
There's no limitation. I mean, you can easily run also just with the lower extremity, and there are such examples in our model repository.
And then related to that, is AnyBody suitable for upper body analysis, for example, for playing a musical instrument?
Sure, that should be doable.
Right. And a similar question, are there any limitations in terms of motions that you can analyze? I mean, that is maybe also connected to force plates, because from my understanding, now today we use force plates, so we know exactly what the interaction forces with the environment were. But when I think about any movement, of course, there could also be situations where there are no force plates. What are the possibilities without force plates?
Yeah, so I mean, it's possible if you have measured the entire body, so full body marker set. I mean, it's possible to predict the ground reaction forces. So meaning that you basically, it's not constrained to have the force plates. Yeah. Yeah.
Okay, but then we would be required to have the full body, of course, because you need to know what sort of forces are coming, carrying.
Yes.
Yeah.
Yes.
So in general, then it's probably correct to say the best approach would be if you have other motion to make sure that the other objects are clearly defined in terms of mass, properties, inertia, or you measure the forces that are the contact forces.
Yeah. Another thing, I mean, if it's about any motion, so basically what we simulate is skilled movement. So it's something you know how to do, and so it's not sort of intended to simulate, let's say, that you stumble over things or a fall or something you've done in a non-skilled manner.
Mm-hmm. Okay, is that, and that I imagine is related to sort of the algorithms you use to predict muscle forces and so on.
Exactly. So it's based on that you do it optimally. That's all based on optimization.
Of course, yeah, that's a good point.
And then that's not the case if you don't, for such cases.
Yeah, with perturbations and good point. Yeah, thank you for all these great questions. It's keep sending them in. I'm great to have so much interaction. Could you show where we can download an example C3D file? Because when loading the file, I get an error. Yeah, there are example files included in the repository on GitHub. We will share that link again afterwards when we send out the recording. And I would definitely recommend that you use this marker set. It's called John Doe in the folder that you can download from GitHub. And these have been tested and should work. And if they don't work, then it must be a setup issue with versions or anything like that. Then please get in touch with us. But I recommend trying the John Doe dataset that's included in the GitHub example if you want to troubleshoot and compare. Is it possible to import frames of hand tracks, I think, or other devices from QTM? So frames, I'm not sure if it's a physical frame here or the data. Maybe if the person is still in the audience, you could specify what you mean by frame. Because I think if you have a hand trail and you have like physical objects, of course, that's possible, I imagine. Maybe we see we've got time for maybe 3 or 4 more questions.
So there's a question here: how does using a lower body marker set excluding upper body affecting the model scaling? Do I need to adjust the scaling factors of the model? So basically, I mean, of course, if let's say if there are no markers on the arms, I mean, when you then, load the AnyBody model, you simply put in a statement saying, okay, I don't want to consider the arms, so it takes off the arms entirely, and then of course you don't need to think about scaling of those. So basically, in general, I mean, you exclude the parts that you don't have markers for.
Yeah. Okay. Yeah, there's another question about example data. And again, I recommend the GitHub example file because it includes example files. If you require a trial license from Qualisys, get in touch with us. Assume it's similar with AnyBody,
Yes.
that a trial license, that you can get familiar with it and experiment with it. So we'll send the link to these files again. Is it possible to model a person with a prosthetic leg? How would the prosthesis affect gait?
Yeah, I mean,
Sir, I need your help with that one.
Yeah, I mean, you could also include, I guess you would put markers on the prosthetic leg, and you could include that in the tracking. So like you could create an extra segment in the model that you put markers on for that prosthetic leg, and you can have the forces flowing through the prosthetic leg into the AnyBody model. But of course, I mean, you would need to put really markers on that new rigid body and do tracking in the same way that we do for the bones.
And then, I mean, it's good highlighting that we are very flexible in terms of the marker set, because our automatic labeling can be trained completely from scratch very easily on a custom marker set. So the labeling part would be straightforward. There's another question about extra markers. What if I have more markers? Can I define the location of extra markers? And I think we can I will just share the screen one more time, because I imagine that this would be very easy to do in the definition that we've shown earlier, to have additional markers here.
Yeah, so if you have another marker called, let's say, head 2, I mean, you would simply copy this piece of code that is highlighted here and basically just rename it to head 2, if that's the name, and give it a new SRL position. And that's kind of it.
Yeah, and this is like the typical position relative to the origin of the...
Yes.
Yeah.
Yeah.
Mm-hmm. So I hope that answers the question. So can EMG data be used also as an input, or for the question was about EMG informed modeling?
Yeah, so I mean, it's possible to read in the EMG data and use that to constrain, to act as a constraint to certain muscle, either individual muscles or several muscles. So we can basically put in a lower bound that was and an upper bound that would sort of limit the freedom for the muscle activation in the optimization to do whatever it wants, but sort of to stay within let's say plus minus 5% of how the EMG was recorded, for example. So it's basically the muscle we will keep, even though the muscle would be recorded, the EMG we would keep it in there, but we would put in lower bounds and upper bounds that would limit the freedom of the optimizer to do what it wants to do, and it would make it follow the measured EMG closer, and you can decide sort of how close that should be if you want that 5-10% slack or less.
So it's essentially more like a boundary conditions that you're setting. It's not directly an EMG driven optimization or anything like that. It's more boundary conditions.
Yes, correct.
So we got some clarification, and I learned a new word here, truck, and thank you for providing the German word as well. So it's basically like this small trolley that people use to move like heavy items. So it's a physical object, and I think you can import, I mean, physical objects into AnyBody. And
yes, sure. I mean, as you saw, I mean, in the slide I had, I mean, there was a lower extremity exoskeleton. So I mean, you can create physical objects directly in the script, or you can, if you have a CAD model, you can take it through a SolidWorks converter from SolidWorks into our modeling language.
Yeah.
So that is absolutely possible, and it's one of the strengths that we have, is that we can do this combined simulation of both these, I mean, the human and whatever physical objects he's interacting with.
Thank you. And as a side note, you can also, if you have a graphical file, like a object file that just representing the look of what it is, you could also import that in QTM, which we found very useful sometimes in presentations and to visualize data. But if you are using AnyBody, then of course that visualization will be more powerful. Another very, I think, relevant, good question is, because it's a trend that we are also seeing at Qualisys, is there an easy way to show the results in a report for therapists without too much processing time?
Yeah, I mean, so we don't sort of have a report generator in our software. So you will have to sort of, but of course you can create sort of output files or that represent data that you that you always look at maybe, and you can then export these files. It happens automatically, and you can import them in, let's say, in Excel or similar. But we don't sort of provide like a report tool within our software. Our software is sort of very generic in that sense.
Yeah, and also on our side, I mean, we have a lot of reports for gait analysis, but at this point, there is no easy route to get the AnyBody results into a software like that. But we do see this trend and for many people, and also, like you can see in the example we are showing today, that if you have a good marker set, correct marker placement, and the model is defined accordingly in AnyBody, the processing becomes a very easy plug and play, just a few clicks analysis. So at least from that part, we are very close to it already. Then there is processing time, which is like passive processing time where the computer is just running. So I think we will be monitoring this and see how much interest there is, because if these measures of muscle or simulation results become more a standard thing that is used in for example, in the clinical decision making or in the workflow in the clinics, then of course that is something we are very interested in. So thank you for the question. Can I increase or decrease the degrees of freedoms at the joints?
No, I mean the joints are as they are. You could say. I mean they. There are, if it's a spherical joint, it has, full freedom to rotate. But that said, I mean, we do have ways to put on joint limits in the model that will constrain it to go into, unrealistic postures. And that can sometimes be helpful, to constrain the model from misbehaving. But basically, it will. Yeah, so it will try sort of to stop the model from going into wrong posture. So yes, it is possible to add joint limits, and there are templates in the model that makes that easy to enable.
Yeah, and maybe it's also good to say something about the complexity of the joints, because I mentioned that the knee joint in your standard models is not a simple ball and socket joint, I imagine.
No, I mean, actually, the knee joint is in the standard model. It is a revolute joint, so it is quite simple. But of course, it's possible to if you're into knee joint modeling, it's possible to do, of course, more advanced joint modeling that accounts for the contact between the bones and the ligament forces and so forth, but that's sort of an extra level of complexity it adds, and it's something you that type of simulation you do if you have sort of special interest in the specific joints.
Okay, I think we are getting close to the end of this, but I think we'll have 3 more questions. Again, a question that's related to the clinical use, or more like clinical cases, looking at patients. And the question is it possible to predict the knee joint reaction force in patients with deformities, such as cerebral palsy and other deformities? The lack of ligaments often results in an overestimation of joint reaction forces.
Yeah, so I think, of course, it's one of the more difficult cases, but there are sort of tools in the software that allows you to, as we just actually touched upon earlier in one of the other questions, to add sort of constraints to the muscle activation. So if you know that this person has specific conditions with the muscle activation, it's possible to use this bound sort of to get more realistic simulation for that type of patient.
And I mean, that is also where we have to be realistic with the patient reporting, of course, that it could, I imagine this is something that could work well in rehabilitation scenarios where or like scenarios where without deformities, because then it can become like a just push button exercise to generate the reports. But as we can see from this example, then it does require some more skill to make sure that the model is representing the properties or the condition of the patient correctly.
One thing that we didn't show today, I mean, in this setup is so this model you have seen today, it sort of scales linearly, so based on the markers. But if you have sort of bone geometries from a specific patient, you can non-linearly morph our model to become that that patient more realistically, so you can bend the bones if sort of non-linearly if that is needed.
Mm-hmm. Okay, last two questions. I think they're two short ones to wrap up. And if there are any other open questions, we will be answering them via chat or via email if you have not posted anonymously. So should the static trial be done on the force platform? I think I can answer that. Correct me if I'm wrong, Søren, but for the static optimization, that is fitting of the model and there's no force involved. So the only scenario where you would want to have it on the force plate is if you actually want to analyze balance or something like that, or how the person is standing. Okay. I could see you nodding, so that's good.
Yeah.
And last one is a question about frame rates. So what sort of frame rates are required for different types of movements? And that is really going to the data collection part, to the cameras. And that is very much depending on the type of movement, of course. We have cameras running up to 300 hertz, 500 hertz. So it really depends on what type of movement you're looking at. And then you have to think about sort of the frequency content of the signal of the movement that you are analyzing. So if it's a very smooth movement, slow movement, then today we were running at 100 hertz, which is perfectly fine for a gait scenario. But in many sports scenarios, we see that it is required to use higher capture rates simply because you have so fast changes. So I would recommend to look at the Nyquist theorem as one thing to check out for this if you want to look at the frame rates that are needed. Okay. Yeah, any other open questions we will answer by email. I can see a few more here, but we can see your names, so we'll be happy to answer those by email. And with that, I would like to thank the AnyBody team and especially Søren very much for being part of this today and providing all these insights. And I will close down the webinar, and thank you very much all for joining. Bye-bye.
Thank you.